Okay, so the first 3 problems for our quiz review, and we will have a test for, I'm not sure actually if we'll have a test for 30 through 40. This will probably just be our quiz for pages 30 through 40. All right, we have given the tan x equals -5/8 with x between 90 and 180. Find the exact values for sine x and cosine x. All of these problems will be without a calculator. Okay, so step 1, draw our circle. Okay, and what quadrant are we looking at here? Quadrant 2. This is just a problem we're doing for the quiz. So here's our theta. All right, we draw a reference triangle. And remember, this theta is going to have the same value as the theta here. Just the quadrants are the only thing that determines, if it's positive or negative. So since it's in quadrant 2, we've done this a million times. All students take calculus, so therefore tangent is negative in quadrant 2, and we knew that from here. So we take the value of tangent x, -5/8, and how do we incorporate that into our reference triangle? Alex?
The opposite side is 5 and the adjacent side is 8.
Perfect. The opposite side is 5. The adjacent side is 8. And again, since we're dealing with tangent here, we already know it's negative in that quadrant, but the reason why is because our adjacent side is going into the negative direction. So if we need to find sine and cosine, then we just need to have the hypotenuse. So we can use Pythagorean theorem to find the hypotenuse. Square root of 5 squared plus 8 squared. It is a -8, but we square it's going to be positive anyways. So that ends up being square root of 25 plus 64, which is square root of 89. And just leave it like that. We want an exact value, square root 89. So now that means that sine of x equals what? 5 over root 89. And I'm okay with you leaving it like that. All right. And then cosine x equals, what would that be? -8 over root 89. Now, this is a question that will be on the final. The only thing I want to be careful of is on the multiple choice parts of the final, sometimes they rationalize your denominator here, which means that you can't have the square root in the denominator. So that just means you have to multiply top and bottom by root 89. So your simplified answer would be 5 root 89 over 89. And 5 doesn't go into 89, so that would be your final answer. And then same thing for cosine. It ends up being 8 root 89 over 89. That doesn't look simpler to me, so that's why I'm okay with these 2 answers. Questions on that one? So here, this is calculator without a calculator. So it says simplify the following using only positive exponents. Okay. So A here, what's the first thing we want to do? Yeah, distribute this exponent. And you have to be careful. You can only distribute exponents like this when it's multiplication here. If there's a plus sign in here or a minus sign, you couldn't do it. So let's use purple there. So we can simplify that to 9 x to the 6th, and that'll be times 3x to the -4. Now we can multiply coefficients. When we multiply coefficients, then you get 27 x to the what? Second. Pretty simple. Again, this should be semi-review. You've done exponents before. But the whole idea is we're getting into logarithms. And logarithms are the inverse of exponents, pretty much. So, at least exponential operations. Okay, B. Okay, the first thing I would do is divide out numbers, the coefficients out in front here. So that would put a 3 in the denominator. Now, there are a lot of different ways you can think about these rules of dividing exponents. The way I think about it is when you have negative exponents and you move them to the opposite side of the fraction bar, then it makes them positive. So that's one way you can think about it. So we can actually think about it as moving this x to the negative 4 up to the top. That becomes an x to the 4. Moving this x to the negative 2 to the denominator, oops, becomes a positive 2. And then the y's will just stay the same. Again, there's a lot of ways you can think about it. This is just how I work on it mentally here. And now we can cancel or divide out, since we have x to the 4th in the numerator and x squared in the denominator, what's going to happen to our x's?
It'll become x squared on top.
So x squared in the numerator, and then what's going to happen to the y's?
Y to the 3rd on the bottom.
Y to the 3rd on the bottom, denominator. That's your answer. Okay, on C. C is a little bit different. I don't want you to have to multiply this all out. There's a reason that I made this non-calculator, because I want you to think about how exponents work a little bit. What do you notice about the base numbers there, the 2, the 3, and the 6? What do they have in common?
They all go into 6.
Yeah, they all go into 6. So if we break down 6 here, okay, isn't this the same as doing 2 times 3 to the 4th power? Same thing. Okay, now we can, just like we did here, see how we distributed in a way that exponent to the 3 and to the x? We can do the same thing here. So what ends up happening is that equals 2 to the 4th times 3 to the 4th. Okay, that's just this part right here. We can multiply in this stuff. So it'd be times 2 to the 6th times 3 to the 6th. And then you would get 2 to the 10th power and 3 to the 10th power. Ooh, interesting idea here. If you think about it, we can kind of factor that out, right? Kind of doing the same thing we did right here. Wouldn't that be the same as 2 times 3 to the 10th? Right? It's the same movement we did here. So the answer would be 6 to the 10th. Now you got to be kind of careful. You couldn't do that. You can only do that because they both have a power of 10. So if they both don't have power of 10, or like if this were an 8, then you're kind of in trouble. Like there's no reason to factor it out to that because you can't make a 6 there then. Okay? So you can only do that if you have powers that are the same. Okay? Otherwise, you could have just left it at this point, like 2 to the 7th, 3 to the 10th. I wouldn't have wanted to go further than that. So you're going to have 2 of these under one problem. Write a plausible equation for this for the graph using sine and radian mode. And I'll give you some ideas here. You know, I'll give you some points like I did in this graph. Okay, so we have 3 points here. We're using the sine. So mentally, I'm just thinking, okay, first of all, I know the sine looks like that. Okay, so I just want to see where that is, where that starts. And if I look at my graph here, I see it starts right there at 0, 2. So I want to first think about what's one oscillation of that sine graph. Where does it end? It looks like it ends about right there. Okay. And actually, you know, I'm going to pull in a little bigger picture. I'm seeing I want a better picture of this, so hold on for a second. Okay, I'll give you a little bigger window on this graph, and you'll see why I did that in a second. So first of all, we have, if we look at our sine graph, it's going to look something like A sine bx plus c. That is the form that I would have that in. And y equals, I'll put y equals. So y equals, okay, what's the first thing you notice about this sine graph? Where does sine usually start? It starts at 0, and where did I start? 2. So what does that change here? The c is going to be 2. I shifted it up 2. Okay? Now typically, the amplitude, which is this right here, you know, right here, usually on our typical sine graph, that's at 0, and that's at 1. Down here's at -1. Okay? How is this one different? It goes from 2 to 6, so your amplitude is actually 4. So it goes up 4, and it goes from 2 downward, it goes from 2 to -2, which is also 4. So that is going to be 4. And what does that affect? A. So we have 4 there. So here's our amplitude. That's 4. That equals A. This right here, your starting point, that equals C. So now we have 4 sine. The last thing to look at is our period. So typically a sine graph in radian mode, where does that end right there? Or in degree mode. We're using radians, but sometimes you think better in degree mode. How long does it take for one oscillation in a sine curve in either mode? 2 pi. So that is 2 pi, which also equals 360 degrees. That's how long it takes. And the reason we know that is because you think about the unit circle, it goes around once, typically, right? It goes around once to do the sine curve. So if we look at that, our typical oscillation is 2 pi. If I look at my graph here, 2 pi ends right there. That's 2 pi. So how many times does it oscillate before 2 pi? 3. 6. Okay, 6 and a little bit more is 2 pi. Right? And you're like, well, how do you, a little bit more? Come on, that's not very good. Well, I know that I'm first of all, in this question, I'm not going to give you an equation that has like some crazy b here. It's going to have an integer value, or maybe like a nice like 0.5 or something. So when I shorten it up, I'm going to shorten it up by 3 times or lengthen it by 2 times or whatever. So if you look at our graph, that's 1 oscillation, 2 oscillations, 3 oscillations within the typical period of 2 pi. So that's going to change our b to 3. That is our function.
So 2 pi is a little bit more than 6.
Okay, now it's the same idea, but now we want to use cosine. And we want to use cosine in degree mode. Okay? So again, I'm thinking about my general idea right now of cosine being A cosine bx plus c. All right, we're going to add a little, there's one more dimension we have to add to this after. But if you have these three, you're almost there. So if I look at this, first of all, I think about my typical cosine. Usually looks like this. And again, just compare it to the parent function of the cosine. It typically looks like that, where the height here is 1, it starts at 1, and goes to -1. Okay? So now, first of all, think about the center. I mean, it's tough to think about the center, but this is the center of the graph. Okay, it starts at 0. Where's the center of this graph?
4.
-4. So how does that change our equation?
It's a down 4 and a C.
Down 4 on the C, so the C is -4. Okay? Now from here, this is our center. Our amplitude is right there. Okay? So what's that distance right there? 0.5. So what does that change in our equation? A. So it's 0.5 or a half. So y equals 0.5 cosine. Now, typically our equation here, our period is how long? In degrees. 360 degrees. I look at my this graph and I say 360 is right here. That's 360. So how many periods do we have before 360?
3. 2.
2. So that means our B is 2. And usually put parentheses around that one to show that that's part of the cosine. Okay? Okay, that also just a little side note as far as this oscillation is called a period. As one period. Okay. Okay, the amount of times how many periods it has in 360 is a frequency. So this is a frequency. This frequency equals 2. Frequency equals 2. Hence this 2 right here. All right, questions?